Hello and welcome to another video. In this video we're going to be doing the weekly contest 392, and I'm just going to go over all four problems. They're all reasonably simple and I'm just going to do them all in one video. So in the first one, pretty straightforward. You're given an integer array of nums and you want to return the length of the longest subarray, which is either strictly increasing or decreasing. So you can basically break this down into two problems. You can first find the longest subarray that's strictly increasing, and that's pretty straightforward. So you just keep track of like what number you're on, and does that number keep increasing? So like here it starts at 1, here there's 2, and then every time it's not strictly increasing, you just reset your length. So like we'd have like 1, 2, and then we'd reset here to 1, and then we'd reset here to 1, and reset here to 1, and so on. So you just have a increasing counter, and then same thing for decreasing counter. So you just have like for decreasing, this would be 1, then this is increasing, so you reset, so it's 1 again, and now this is 2, and then you reset, so it's 1 again, and now this is 2, and so on. So pretty straightforward. Just keep track of, are you increasing or are you decreasing, and at every single iteration, save the maximum of those. And I initialized my initial number to infinity to make it start increasing, but it doesn't really matter. You don't really need to do that. You can make it whatever you want. Yeah, so that one's pretty straightforward, not too much to say there, and it's, yeah, should be pretty easy if you're doing contests. So let's go to the next one. So this one, honestly, the hardest part about this one is figuring out what they're trying to say. This took me like 5 minutes, and then once I figured out exactly like what they're trying to say, it's a really easy problem. So essentially, if you have two strings, A, B, and C, D, the distance is you take every character at the same index and you figure out like how far apart they are. So here it would be 2 and here it would be 2, and it's also cyclical. So what I mean is like you go A to Z and then back to A, so it's like that. So you can either go down, like we can go A down to C, or we can go from A to C by going backwards, and then whatever the smaller one is the distance. So we can go like from A to Z to, so on all the way up to C. So pretty much all we need to do is we have a K of, so I think K is like let's see here. K is distance. Oh yeah, so we want the smallest string we can get, such that distance is less than or equal to K. So distance is pretty much how far we can change our letter. So for example, if our K is 2, that means we can change our letter. Like if we have an A, we can change it 2 letters. So we can either go from A to C, or we can go backwards. So we can go, so it's like W, X, Y, Z, right? So we can go to Z and then to Y. So forward we'd go to C, backward we'd go to Z, or we'd go to Y. And that's basically the whole problem. Is you just, and the other thing is the lexicographically small string. So you basically want to just be greedy here. You want to start at the very first character, and you want to see, do I have enough to turn it into an A? And if I do, then I do that, and then I do that next character until I run out of operations. And so there's a few cases here. So for example, let's go through some of these. So for Z, B, B, Z, and we have 3. So we want to turn this into an A because just like the smallest number, the most significant letter affects it the most, right? So if we have like A, Z, 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 that's smaller than B and anything else like this, right? So if we can get this first letter to change, like that's where our priority should be. And same thing with all the other letters. So here we want to try to get this to turn into an A. And that takes one operation. So it's essentially just need to think about like operations of how to go from one letter to another letter. So remember we can go backwards, right? We can loop like this. So this Z to turn into an A takes one operation. So now we have 2 left. Now we try to turn this into an A, 1 operation. Now we have 1 left. Turn this into an A, 1 operation. Now we have none left, so this is our answer. So let's go through the next one, X, A, X, C, D. And K equals 4. So obviously you want to go down, so it's like X, Y, Z, A. So to go from X to A takes 3. So we'll turn this into an A. Now we have 1 left. This is already an A, so we don't need to do anything. And now here, we can't go all the way to an A. So because we can't go down to an A, we have to actually make this as small as possible with the operation we have left. and all we can do is just make it the letter before, right? So we just change this into a W. So if we can't go all the way to an A, like if we need to figure out like cost going down to A. And what I mean by down is like, let's say we're on an X. How long does it cost to go like this way, right? X to Z to A, and the cost of going backwards to an A. And then if we have one of those, like whichever one's cheaper and we have enough, we do that. And if we don't have enough, we just go up to whatever letter we can. So for example, if we're on X and we have or let's say we're not on X, let's say we're on like M, and we have like 5. We obviously can't go to an A, so we will just go up 5 letters. So it's like A, B, C, D, E, F, G, L, M. So we'll be at like G or whatever the letter is, right? We'll just go backwards. So if this is like A, B, C, D, E, F, G, H, I, J, K, L, M. So we obviously can't go like this way or this way all the way to A, so we'll just go 5 letters backwards. So we'll go to L, to K, to J, to I, to G, and we'll change this M to a G, and that's what we'll save. And that's basically the idea. You just greedily try to change every letter starting from the front into an A, whichever way is easier, either all the way, either going up or down, depending on where you're at. So obviously X, you'd want to go through Z, and if you have a letter like C, you'd want to go up. And if you don't have enough, you just take whatever letter you're on and you use all K operations to make that letter as small as possible. So let's take a look at that code. Pretty straightforward. So we just have a result. And so I could have probably simplified this, obviously, but I just wanted to like finish everything. So if K is 0, we can't change any more characters, and we just take whatever we have. I made an array, we joined it into a string, and we just return the rest of the string because we can't change anything else. And so I calculated the cost of going backwards and forwards. So going backwards meaning like if we're on like C, we'll go like C to B to A. And forwards would be like if we're on C, we'll go to D to E to F and so on to Z to A. So calculate the cost of going both ways. And then we'll figure out, do we have enough? So if K is, if we have more than or equal to what we need, then we will just append an A and we'll subtract what we needed. Otherwise, we just go back as much as we can, and then we just return the rest of the string because now K will be 0. So probably can get rid of this. I don't know if like K can be 0, but this is not needed. Can simplify a bunch of other stuff, but essentially, yeah, pretty straightforward. Like once you figure out what they mean, that whole distance thing, it's literally just, like it's like how to make a number as small as possible if you can change every digit, and changing every digit by one number takes one operation. You just prioritize the primary digit because that's the one that matters the most. Okay. So let's go to the next one, and let's actually delete this, and I believe I have it over here. Yeah. Okay. So I think this contest was pretty doable. Like I figured out how to do the last one in like 5 minutes. It took me like 20 minutes to debug because I'm kind of like tired or something, and I kept making stupid mistakes. But like the actual logic was like pretty easy. Like it's definitely one of the easier contests. Like figuring out the hard problem in 5 minutes is like almost never a thing. Okay, so here you're given an integer array and a non-negative integer K. In one operation, you can decrease or increase every element by 1. Return the minimum number of operations to make the median equal to K. So essentially here, it's pretty straightforward that you want to sort your numbers. So if, let's say, for example, 1, we sort here. So we have like 2, 5, 5, 6, 8. So our median is pretty straightforward. So if it's odd, our median is just going to be the middle number over here. And basically the idea here is there's going to be one of 3 cases. So case 1, median equals K. We're done, just return 0. Case 2, median is greater than K. So in order to make this median go to K, the fastest way is pretty much take your median, turn it into K. But the problem is that every number smaller than it that is bigger than K also needs to turn to K. Because if this happens, now our median will be 5, right? So the idea is if the median is bigger than K, we need to take the median, change it to K, and every number that's smaller than the median, we also need to change to K if it's bigger than K. So that's why in this case, we need to change this to k. So this is one operation, and this is another operation. So we take every number that's smaller than the median that's greater than k, and we just figure out how many operations does it take to make it k, which is really easy, right? So every number smaller than the median to make it, like if k is 4 in this case, all we'd have to do is just go through every number and figure out like what we'd have to make it go down. So this would be one operation here, and then this is one operation as well. So then we have another case where the median is less than k, which is example 2. So sort again, 2, 5, 5, 6, 8. Now the median is, or not the median, k is 7. So the median here is smaller than k. So because the median is smaller than k, we have to make the median go up. But if we make the median, we want to take the median go straight to k. But this is the same thing. So if I make this go to 7, then the median will be 6. So you basically have to do the same thing. So every number that is bigger than the median now, you have to make it go down to k. Actually, you have to make it go up to k, sorry. Because you're going to increase the median to k, which will move it. So in order for it not to move, you have to take every number that bigger than the median that is smaller than k and increase it to k. Which is also straightforward, just linear pass through your numbers. And just for every number that's less than k, that's past the median, figure out how much you need to make that turn into k. So this is 2 operations, and this is 1 operation. So this is 3. And when I read this third part, I thought this was actually kind of hard. But their definition of median is actually, so if we have this 1, 2, 3, 4, 5, 6, it's pretty easy. So their definition of median is whenever you have 2 numbers, pick the larger one, or I think the second one. So if these two are the same, like it's easy, like you just pick the second one, or I guess it wouldn't matter, but you just pick one of them. You don't have to pick like the middle of them or anything. So if it's like this is the median, and if they're the same, you can also pick the second one. So, yeah, the median right here, middle element. If there are 2 choices, the larger of the 2 values is taken. So, but even if it was like the center one here, like the average of 2 would still be 3, so it's still the same thing. But regardless, so it's easy if it's even as well. You just pick the second one of the 2 mediums. And then same kind of thing. So here k is 4, so we just return straight away. We just return 0. But like if k was 2, then we'd need to make this go down to 2, and then we need to take every number that's smaller than it and go down to 2 as well. So this would be like 1 operation and 2 more. And if k was like 8 or something, then we'd need to turn this into an 8, and every number that's bigger than it, we also need to turn into an 8 that's smaller than an 8. So really, really easy problem once you figure that out. And here's the code, very easy. So you just figure out the location of the median. It's either going to be the middle element or the right of the 2. So if median is greater than k, we just take every single number that is less than the median, and we say if it's greater than k, we're going to add that number minus k, right? That's example 1. So like this is greater than k, we need to make every single number to the left of the median that's greater than k go down to k. And if median is less than k, then we're going to make the median go up. So we also need to make every number to the right of the median that's smaller than k go up. So we just take that operation. It's pretty straightforward. And finally, at the end, I just figured out how many operations it takes for the median to go to k. But that's like the greedy solution, is you make the median go to k, and then you figure out how many numbers on each side need to go to k, depending on these 2 cases. So pretty straightforward. So this is n log n, time, and O1 space. You can probably maybe make some like linear solution, but this was like pretty easy. Okay, so let's look at the last one. Okay, so I think I should have the last one over here. Yep. All right. Yeah, so essentially for this one, you're given a graph, and like it's actually easier to see when we look at the example. So essentially you're given a graph like this. It's unweighted, and you have a bunch of nodes. So you have n nodes labeled 0 to n minus 1, and then you have some edges. And these edges have like a weight, and you're given queries. And for every query, like let's say it's 0 to 3, that means you need to start at 0 and you need to get to 3. And the cost of going to 0 to 3, you can actually take any edge you want as many times as you want. So I can go like here, 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 back like as many times as I want. But I need to end up over here. And the cost is the bitwise AND of all the edges you traverse. And you want to try to minimize that for every single query. And these are kind of big, so you can have 10 to the 5th nodes and 10 to the 5th queries. So you need to probably pre-process. That's kind of a hint because they're both 10 to the 5th. So you need like one solutions for every query, or logarithmic. So let's look at these examples. This will clear it up pretty easily. So if we start at 0 and want to go to 3, like you might think you just go like this, but if we actually go like this, the bitwise AND of all these will be 7 and 7, which will just be 7. So what you actually want to do is you want to go like this, then you want to go down here, then you want to go back up, and then you want to go here. And then you would do 7 and 1. So I'll just do A for AND. 7 and 1. And then you go back up, so and 1 again. And then and 7. And this will give you, let's see, 1. Yeah. So the main thing you have to know for this thing, for bitwise AND, is for bitwise AND, it can only make a number smaller. So if I do A and B, so if A and B are exactly the same, then I will just get the same number. Otherwise, I will basically just get a smaller number guaranteed. Because let's say I have some random numbers like this. If the second number is different, like let's say I have something like this, basically what's going to happen here is every bit that is a 1 on both of them will stay a 1, and everything else will turn to 0. So it'll be like 0, 0, 1, 0. So you're guaranteed for two different numbers to get a smaller result, because everything that has a different bit will just turn to 0, and everything that's the same will stay as 1. So if you know that for a bitwise AND, my number can only get smaller or be the same if they're exactly the same number, then it's pretty straightforward what you want to be doing. So because your number can only get smaller, basically you want to make this graph, you want to record connected components of your graph, so whatever is connected. So like this would be a connected component. And it's guaranteed that if you take every edge possible, that result will be equal to the best result. Now there might be like a shorter path, but that doesn't really matter. So you can just say like, okay, I'm going to have this connected component, and I'm going to take every weighted edge and just AND them together. And so that's kind of the idea for this problem. You basically can just do a union find, and you just, for every component, you just record like what's the bitwise AND of my current component with all the edges. And then whenever you connect two components, you just take the bitwise AND of one of your components and bitwise AND it with the other one. So for example, like if we have 0, 1, and this cost is 7, and let's say, I'm just going to show another example. So let's say we have like 2, 3, and this cost is 2, let's say. So this component will have a bitwise AND of 7, and then because you're doing union find, you'll have like a parent node of this component, let's say this node. So this node will have a AND value of 7, and let's say the parent node of this is 2, and it will have an AND value of 2. Then when you connect them, you figure out which one's the parent. Let's say this is the parent, and you just take its AND value, and you AND it with the other component that you connected to. So you will just do 2 and 7. And that's kind of the idea. You just do a union find, and anytime you add an edge, So the other thing is, let's say this was connected already. So normally for union find, like you only do stuff when you actually need to perform a union. But there is another thing here. Like let's say I add an edge here that's 0. So in that case, what you do is you call union find every time there's an edge. So every time there's an edge, even if you don't need to do a union, you will still take whatever the parent of the graph is. Let's say it's this. And you will take the edge that you added, and you will AND your total AND of your component to this value. So now the total AND here. So for example, like here, the total AND will be a 1. And then you'll be like, okay, well, I put in a 0. So I will AND this with my 0 to get 0. And now the AND value for any nodes in this component is 0. And then the rest of it's pretty easy. So when you do the queries, you just check, are my two nodes in the same component? by just doing a find. Like, is the find the same? If the find is the same, get the and value for this whole component, right? All these edges anded. We're gonna pre-compute all that. And if they're in different components, then you just return -1 like this. And the easy way to handle what do you want to set your and values or your like total value or something of each node in the beginning? Because you're gonna need to and all these, but what do you and all these with to start? Like, do I make the value of this a 7 or something? No. So what you want to do is you can look. So I think in the constraint, the biggest weight was like 10 to the 5th. So basically, you need a number that's bigger than this. That's all ones, because an and of all ones and another number is just that number, right? So like if I do 1 1 1 1 1 1 1 1 whatever, and any number smaller than this, like 256, this will just give me 256. So that's the idea. So you can initialize the and value of every node. I think I initialize it to like 2 to the 20th minus 1, which will just be 21s or 19 or something. Or 21s, I think. Anyway, so that's the initial and value of like each of your nodes. So normal union find, you have like a roots, a ranks, and then I add a ands array as well, and I initialize every value of every node to this, and then whenever I connect an edge, I figure out like what's going to be my root node of my graph, and then whatever the root node of that graph is, I and its current value with the value of the edge. And then the rest of it, that's basically it. So just a simple union find, and then you just have a default and value, and then it's like super easy. So like I figured out how to do this very quickly. I just had a lot of bugs, because yeah, I guess it is like 12 or something for me. So let's take a look at that. But yeah, it's definitely one of the easier by far final ones. So yeah, simple union find. You just have this ands for every single node. This will just make sure that to give it a default value that you can and all your other stuff with. Straightforward find, except there's this one little thing in here. So even if you don't need to union them, you still want to and the root node of your connected component with the weight of the edge. And then the rest of it is just straightforward. But then when you and things, so like if, let's say I connect nodes X and Y, and I make Y the root, then I want to say, okay, I want the value of Y now to be Y and X. I'm not really going to use X anymore because Y is going to be the root, and I also need to and it with the edge that I added. And then the other thing is just the other way. But then yeah, really straightforward problem. So you just, for every edge, you do a union. Then you have a result initialized to -1. So there is one other thing. Sometimes in a query you'll have a node and itself. So like you'll have like 3 3. In that case you're already there, so the best thing to do is just not travel at all. So for that case you need to return 0. But yeah, so this is the case here. So if the start and the end node is the same, then the query result is 0. If the two nodes aren't connected, I just initialize everything to -1, so just leave that there. And if they are connected, then get the value of the connection. I actually probably don't need this anymore because this was this case here. So I think I can just do this. Let's see. I think. I could be wrong. Yeah. So that part isn't needed anymore because that's what I was returning. Because I thought that like if I'm on a node that's not connected to anything, then I want to like return its initial value, or I want to make sure I don't return that like my big value that I have. But that can never happen because you're going to have a connected component. You're either going to have two nodes in different components, which would go return -1, or you'll have a connected component, and then you would have anded your big number with one of these weights already, so it's never going to be like the initial value. So essentially, you just if the nodes have the same parent, you just figure out what's the and value of the parent, and that's basically it. This can be start or end because they'll have the same parent, so it doesn't really matter. Yeah, so pretty easy problem, like very easy compared to most hard. Like usually, I mean, like not super easy, but definitely if I can come up with it in like 5 minutes, definitely one that if you do a lot of contests, is definitely solvable. Like you might have some issues with like mistakes, but the actual concept of figuring out is pretty easy. And then I guess we can talk about like runtime and all if I missed any. So let's see. This one's pretty easy, just O of n, O of 1. This one, let's see. I think this is just like O of n, O of 1 space, also pretty easy. So this one had a sort, so n log n, and then they're at no space. And union find is typically, so union find operations are typically O of 1. And so you basically just figure out like how many edges and how many queries you have. So this would be like edges plus queries or something for time. And then space would be like, so I guess probably like, vertices or something for space, because it's just going to be all these arrays. So it's going to be like O of n here, something like that. But yeah, definitely one of the easier LeetCode contests. Let me know what you guys think about this. And yeah, I do like this format a lot more. Just doing all the videos in one, especially for these easier ones. Like maybe if there's a hard problem that took like 40, 50 minutes, I'd split it up. Or maybe I'd split it up into like 3 problems in the last one. But for things like this, I can easily fit into one. So yeah, let me know what you think. And yeah, or if you have any questions about any of these. And I'll put all this code into the video as well if you guys want it. And yeah, thanks for watching.